out of its thing.
Yeah. So
But that's part 4. In part 4, they ask about that.
yeah, I know, but like if part 3, what am I put? No number because it doesn't.
No, write it as if it would. Write it in a way that write it as if it was in the right thing, and just the next one say it won't work because it won't copy the beginning of the right address.
So you're basically just writing a wrong thing.
Exactly. But
Great.
well, because Nachum joined.
Yeah, hi.
Oh, okay.
Hi.
I don't know what you were talking about, but don't do a wrong thing.
Homework. Well, no, in the homework 3, it says. In homework 2, there's a part where it makes us write a wrong thing.
Really? I don't remember that.
Question 1, part 3, it says to write it in binary, and then part 4 says write why that's wrong.
All right. I take your word for it. I just translated it, so I should remember that, but I don't. Whatever. Wait, let me look at that. That's confusing to me.
It was very confusing.
Computer architecture homework number 2. Right,
Mm-hmm.
I'm looking at it. Let me see my screen. Let me do a share screen. Here it is. So we're recording. So where are you saying? Down somewhere here? Assuming the program starts at address such and such, how will that one? What are you talking about? It's here.
Yeah, sorry, I didn't realize I was muted. Yeah, that part.
Where? Assuming the program starts at address 0F, how will the BNE and the J instructions in the program be encoded?
The BNE will be fine, but the J will have a problem because it will go out of its scope, I think.
No, the opposite, no? The branch won't work because it can't jump that far because doesn't it copy the beginning of its address from the previous thing?
That's
that won't
the jump.
work because I think the binary doesn't the binary branch
Where
need,
is this?
sorry, doesn't the branch doesn't the branch need more data than the jump?
Wait a second. Beginning, assuming this is the program. N is positive, 0 refers to 0. Assuming the program starts at address, okay, it can start anywhere. The program starts at that address. So how will the BNE and the J instructions be encoded? Why should there be any problem?
Because it looks like it looks like it's jumping away out of its scope, so to say.
Because the first 4 bits, as represented by this,
right, will change.
Will have to change when I jump. Well, wait a second. Where is that jump to? They won't.
It will.
No, it jumps back to loop, but at loop it has a change. Yeah.
Let me say it in my words. But by the time I get to the J command, this will no longer be the address, obviously, and it'll already have a 1 over here. And when I try to jump back to the beginning of the code, I will be stuck with that 1 over here, and I won't be able to get there.
So the computer won't realize that, right? It will just go forward.
Yeah, Yeah, well, exactly. The computer won't realize that, and it will go to the wrong location.
It'll be somewhere random.
No, it won't go to random. It'll go to the wrong location. It'll go to, instead of going to FFFFF, it'll go to 01 FFFFF. In other words, it'll change the bits that it can. It'll change the bits that it can change, and the bits it can't change, it's stuck with, which will be a 1 over here. So instead of going backwards, it'll go forward.
Doesn't the branch also have that problem where it will also copy the beginning of the bits? It's not just the jump, is it?
I think the branch is fine.
It's just a jump. The branch has no problem like that.
The branch has because the branch keeps it in the register.
The branch has takes the whole PC as it is and adds it. It just
doesn't
doesn't
have an
add.
offset.
It just takes that, this whole FFF, whatever it is, or it'll be 1 and then 0, 0, 0, something, something. And then it'll just add, it'll just subtract from that what it needs to, and it'll go, and that 1 will drop away, go back to a 0 again, as it does the subtraction.
My question is then only when we have to write the J instruction, do we just have to write it wrong, or should we just say this is not possible?
It's garbage. Oh, I would do both. I would say this is the theoretical encoding, but it will fail. The coding will, I mean, it's an impossible, yes.
No, but I think that question is part 4, where it asks, assuming based on the assumption that you wrote, will the program run?
Given the assumption of a part 3 above, will the program run at all? If not, where will it fail?
I think that's the part where they want us to know.
So that's what he wants. He wants both parts. First, you write what the encoding is, and then you write what the failing is. All right.
That was what we were talking about. That's why we said you
so that was the first.
thing.
So you guys discussed that in 3 minutes, and it took me 10 minutes to discuss it. So you guys are smarter than I am. What else would you like to talk about? Unless you want to, we just start with the material, with the new material. I don't hear any questions.
I just like talking about the homework in general. Makes me figure it out more.
Mm-hmm. Talking about the homework is good. Because, I mean, theoretically, I'm not supposed to talk about the homework. You're supposed to figure it out and realize that you didn't understand anything. But I'm happy to talk about it a little bit, but not everything.
Well, if we did it that way, we wouldn't have probably been able to give it anything, at least not me.
Yeah, fine. So that's fine. Anything else?
Sorry for some guys who just came in now. Yeah, we did have a bit.
Well, I lost you. You went mute.
Yeah, you did have a bit of a problem with question 1, and yeah, it looks like Yitzhak sorts out the problem.
Yeah, he did.
Yeah, so
well, that's what
we're supposed to answer basically the wrong way. It's going to give the wrong answer, right? Number 3
right.
going to give the wrong answer.
In 3, you should put what the encoding should be, and then in 4, you should explain why it won't run.
Right.
Right. Okay. So I don't know. Anyway, let's go to the new material. Where are we? Oh, I lost my page because I went back to see the homework assignment. Where is it? Here we are. You see my page, right? Somebody?
Yeah.
You guys, well, fine. Okay. Let me put that back. I see. We've done this, we've done this, we've done this. Here's where we are. I gave you guys homework also, right? To go over this and to prove to yourselves that this is right. I hope you did that. If you didn't do it, still do it. Still do it after this class right away. Go over this again and see. I think we did the LW. See if the SW makes sense. See if the BEQ makes sense.
Well, again, just SW. What does SW actually stand for again?
Store word. It's the opposite of load word.
Yeah. First you load it, then you store it.
Yeah, you load it into a register, you store it back in the storage. Storage is the data.
An actual data segment.
Right. Data is a huge... What?
I don't understand this chart. I don't understand this chart.
Well, were you in class last time?
Yesterday?
Yeah, I think so. Yeah.
No, we were informed too late, so I didn't realize.
Did you look at the video that's posted? Ah, well, maybe I just posted it. I just posted it now. Anyway, I posted a video on it, and you can look at it. I explained it. I spent about a half an hour explaining this chart. It's on the Moodle. You can look at it. I don't want to do it now because it's going to take so long. But this is the controller This is the orders. These are the what bits the controller has to light up on this chart. This is a diagram. Now this, okay. Let's talk about the controller. The controller has to put certain numbers on these lines to tell what different units do, what their jobs are. In other words, if this is going to be, for example, an add or a subtract, this ALU, he has to know whether he's doing addition or subtraction. That I'm just giving you a quick, for the benefit of whoever wasn't here yesterday, quick example of a summary is this is the ALU. It does addition of the two numbers that come out from this register, from this register file. Now, he has to know what to do. Should he add or should he subtract? Or do something different? So this controller, this guy gives him a message here, a 1 or a 0 or 2. Actually, I think it's 2 lines, 1 and 0, 0 and 1, or 1 and 1. Gives him some kind of message telling what to do. And how does he know what to do? Well, he gets a message from the big controller, and he tells him what to do. That's what this line is. And the controller itself, how does he know what to do? Well, he gets from the command that we gave him, this is the instruction. This is the actual register that has the instruction. And we have the instruction and the opcode, which is, of course, what the command is. Is it add or is it subtract? The opcode goes right into here. The controller reads the opcode and does what he needs to do. No, I'm teaching right now. Wait a second. Let me. What if I go? Wait. Just a second. Why can't I stop recording? Oh. I can't. Ask. You have to go by yourself. I'll help you. Just a second, guys. I'll be right back. Okay, I'm back. So the instruction goes right into the controller. He gets 6 bits of instruction, and based on what those 6 bits are, he knows what message to give to ALU. So this is the table that shows that. This is, see, it says op5432110. Those are the 6 bits of the opcode. The opcode comes in, and this is a.
Those AND gate. Those are AND gates, right?
These are AND gates with actually NAND, I believe, with that circle there. Well, they're AND gates, basically. Sorry, I take it back. They're AND gates. When some of them, I've noticed, some of them have zeros and some of them have ones. I mean, some of them have little circles, some of them don't have little circles. So what this means is that this AND gate. So what these lines mean, first of all, is that whatever is on this opcode line 5, whatever is on bit 5, if it's a 1, that 1 is going to go to this guy, and to this guy, and to this guy, and to this guy. That's what this dot means. This black dot means that there's a fork in the road, and as Yogi Berra said, if you come to a fork in the road, take it. So you come to this fork in the road, and you take both ways. You take it. You go down and you go over. You go down and you go over. So we're dividing that signal is going to everybody. Every signal is going to every AND. Now this AND gets it. And what he gets is actually it's going to be the AND of not. The circles here mean not. So that means this will only produce a 1. This AND will only produce a 1 if everything is 0. When is everything 0? Who can tell me?
With R command.
Exactly. If it's an
R,
R-type command. Remember that every R-type, the opcode is 0, and the function code tells us something what to do. So if it's an R-type, the zeros, these are all zeros. This will be a 1. And that 1 will go through to register dest. It'll also go through to ALU op. So if we go back over here and we look, we see that ALU op is written there, and that's going to go until the ALU 1. Well, there's ALU op and ALU op. There's ALU op 0 and there's ALU op 1. Here, ALU op 1 will be 1. What will ALU op 2, ALU op 0 be? Well, we didn't explain that yet. Depends on this. But you get the basic idea. This is the logic. This logic, we've put knots in certain places, and we put ORs over here, and we did all of this in order to get the right signal on the line so that what we explained yesterday would work. In other words, the signal comes in, and now we're describing those lines, and how exactly does he send the right signal? Remember, we wrote a 1 and a 0 on some of these lines. How does he get the 1 and the 0? He gets it because of these logic gates. Signal comes in. If it's all zeros, a 1 is going to go here. But what about the register right? Well, that depends. He's going to get a 1 here. So actually, since that's an OR, it's also going to be a 1 there. Well, that makes sense because every register right, every R type is also going to write to a register. That's why register right.
Is this complete? Is this diagram complete, or are there only 4 different opcodes that make a difference to the controller?
This might be, that is a good question. It's certainly complete enough for what we've described up till now. We haven't explained, for example, we don't really explain certain commands, like a jump register. Certain commands are not fully explained. But yeah, this is complete. Not too complicated.
Why are those AND gates over there?
Why are they here? Because if I put them over here, it wouldn't work. No, it's a joke. It's like saying, if your kid asks you, why do children have to go to school every morning? The answer is, because the horses don't fit through the door. That's my joke. Why do children go to school? Because we tried to send elephants to school, but they won't listen. Anyway, why is this AND here?
Why are those AND gates?
I don't understand the question.
We want. Oh, they're like. Are we missing? What are we? Oh, are those little circles? Those are knots.
That's what I said.
Ah, okay, fine. So I missed that. Sorry.
These little circles are knots.
Okay.
This is an AND. These are all zeros. They turn to 1s, and I've got a 1 coming out here. Now this one, this line will obviously be, if there's a 1 here, this will have to be a 1 here, a 0, and a 0 in these 3 places, and then 1s in these 2 places. And in that case, this will produce a 1. So you see that these operation codes that we have are not just random numbers they picked. When they pick, 34 as a load word and 43 as a store word, it's because they wanted to light up these lines here. You know what I mean? To produce the right results over here. So sometimes you may ask yourself, why is a store word and a load word, why aren't they not adjacent numerically? And the answer is because the engineering works out better this way. Because those numbers, you think of them as as a decimal number, but really I'm just looking if I have this. No. Anyway, you think of them as a decimal number, but really they're lighting up these electric cables, and we're using these things. And of course, we could have built these ANDs differently, and then maybe we had different numbers to get the desired result. Anyway, I don't need to go through all of them, but you see the basic idea. ALU control. The ALU, oh, so now when we talk about the ALU control, what we're talking about is this guy over here. How many signals does he get and how many does he produce? And what are they? So the ALU receives the 6 bits of the function field of the command. Right. So the ALU receives the 6 bits of the function field of the command. That means if it's an R type, then here, let's look at this picture. Here, I'll be right back. Maybe somebody can, maybe one of you guys will volunteer for the next 2 minutes to explain why, if it's an R type, the ALU gets the function.
Here I go, Zach Schutzer. The ALU receives that because the R type has an opcode of 0000, and when the AND gate receives it, it knots all of those zeros, sending a 1 to the ALU control. Zach Schutzer, signing off.
That was good, Zach. You should answer more questions like that.
Always here to serve.
All right. Does somebody need an explanation still? You're okay? Somebody give me a confirmation. Is somebody breathing there? I see a cat. Hello?
The cat's Ellie.
We're here. You're there. Okay. So we're going to talk about like how the controller controls the ALU, or how the 5 bits that come in over here, the instruction, how they control the controller. Let's see. So the ALU receives the 6 bits, sorry, the 6 bits, not 5, of the function field. Based on this, it determines what operation to do and send a 3-bit code to the ALU instructing it what to do. Here is the table of instructions that the controller sends to the ALU. So before we even talk about how we control the ALU controller, what signals does it send? In other words, based on this input or this input, he's got 2 input lines, this arrow and this blue line. Based on those, he's going to send a 3-bit instruction to the ALU. What are those possible things that he could send? So these are the possibilities. He can either send 000, in which case it means he wants the ALU to do an add, or 001, which means he wants an or 010 means this is an and, sorry. This is an add. And 110 is a subtract, and 111 is a shift, is a set less than. They can also do a set less than. Those are all the things that I could tell the ALU to do. What does the ALU do when there is no function code? So if it's an R type, what I explained is that if it's an R type, he gets this function code here, this instruction 0 to 5 is 6 bits. That tells him what to do. What if there isn't, if it isn't an R type? Well, then as I said, really, you're so smart. Very good. I'm working now. I gotta do this now. No. Yeah, you can go. I think they're busy now. But ask Lovie to help you. Okay. Now, this line comes here and controls it. So what does the ALU do when there's no function called? For some commands, notably L, W, and SW, the branch commands, the 6 bits of the function field are used for the offset, right? They're not available. They're actually part of the offset. So how does the ALU know to ignore that function field in such a case? There's gonna be data on those 6 bits coming in, but he has to know to ignore them. To solve this problem, we add a 2-bit input to the ALU controller called the ALU operation or ALU op. This value, when not set to 210, will override the normal ALU controller value.
Why do we need it to be 2 bits? Wouldn't 1 bit be enough?
No, because we have 3 options. Either we tell it ignore the function, and if we tell it don't ignore the function, then we still need to tell it what to do. So we need at least, a 1 more bit for that. See what I'm saying? Let's say we have 1 bit that tells it ignore.
Knowing what to do comes from a different field. It comes from like func field or something.
No, but let's say it's not if we tell it to ignore the function field, then it has no way of knowing what to do. If the function field is what tells it what to do, we happily go and tell it ignore the function field, but the ALU still needs to do something. So we need 1 more line to tell it, in that case, what should you do?
And then we only have 2 options, right?
And then we're gonna only have 2 options because we only have 1 line.
What are those 2 options?
Well, we're gonna explain.
Okay.
Let's go in the order of these slides. So we added 2, but I answered the question why we need 2 bits. So when it is set, when it's not set, with this value when not set, so when it is set to this, you're gonna set it to 2 when you want to take in that function field and do what the function field says. But if it's not set to 2, then we're going to override the normal ALU controller behavior. In other words, we're going to override the fact that it looks at the function field, effectively causing, right? And then for an SW, or an LW, the ALU will need to add the offset of the register, of the RS register, to get the memory location, right? It's going to need to do that offset plus pointer. So it's going to need to do an addition. And for a BEQ, it's going to need to do it as subtraction. Why? Because to check if something is equal, you need to subtract them from each other. If you want to see if 7 equals 7, you say, well, 7 minus 7. If it equals 0, then they're equal. So we need to do subtraction. So basically, for the SW and the LW, we're going to need to do add, and for the BEQ, we're going to need to subtract. So there's only 2 options, either add or subtract. So we have 1 bit will solve all of our needs. So 1 bit to tell it whether or not to ignore the function field, and 1 bit to tell it if you are ignoring the function field, here's what to do. Makes sense. So now we're looking at the ALU controller outputs. So if it's opcode 35, then that means it's a load word. Then that means we're going to ignore the function field. That's why there's a line there. and the ALU out, the ALU op, the 2 bits of the ALU operation coming from the controller will be 0, 0. And that will mean that the ALU should be sent the bits 0, 1, 0 in order to do that add. And the same thing for subtract, for store word. But for the BEQ, which is a different opcode, obviously they're all different, then now here it'll be different. The ALU op will be 0, 1. So we're going to see that 0, 1 is saying do a subtraction. So 0, 0 means do a, yeah. You can take off the shirt if you want to get. Bring me another shirt and I'll help you put it on. Bring me another shirt. Okay. So again, if it's 0, 0, he's going to do an add. He's going to set these as apples. If it's a 0, 1, he's going to do a subtract. And that's it. And all the other cases are 1, 0s. Well, the 1, 0s say, look at the function. And the function will tell me what to do. In other words, if it's 1, 0, the reason why it's 1, 0 is because it's an R-type command. You got a 0 in the opcode. That told him to set the ALU to be a 1, 0. And for all the R types, it's going to be 0, and it's going to cause the opcode that he receives, the ALU operation will be 1, 0, which will mean depend entirely on what this field is, on what the function field, on what the 0 to 5 bits of the operation are. If it's 33, do an add. If it's 34, subtract. 36, do an and. 37, an or. 42, an SLT, and 32, an add. So in other words, we're using the function field when it's a R type. And then the ALU will know to look at the function field because you got a 1, 0. That's what I said over here.
Where does the function field come from again? Those are the last 5 or 6 bits of the
they're the first.
command?
They're the first. Well, the rightmost.
The
They're
right
the
side.
rightmost bits of the command.
From bit 0 to 5.
Exactly.
Sure.
Oh, the other one from the back. Not too hard. Sorry, guys. My wife is working late all week.
Well, it's a good thing it's the end of the week then.
Oh, do it. Let me try again. Slow. Like this.
I have a question for when you're ready.
Maybe somebody else knows why is the opcode and the function numbers, like, why are they those numbers? 35, 43, 4.
It's based on the actual circuit boards. That's what he said. He made it sound like we're gonna only see that soon when we actually get the fuller picture.
I hate to wait.
Does anyone know when this class is going until?
I would guess 7:30, but I also want to know.
All right. Questions?
Yeah, I have a question.
Yeah.
Or 2 questions, actually. First question has to do with material. So when we ignore, or not when we ignore, but when the function code becomes part of the offset, it becomes the least significant bits of the offset? Like how does it get added on to the offset?
No, it becomes the least significant bits of the offset, yes. In other words, the offset is bits 15 to 0. 0 bit being the 0 bit of the function code. But now it's the offset. So 0 to 15 is we take those, we add 2 zeros, we sign extend it, and then we shift left 2 spaces.
Right.
Branch.
Okay. Also, until what time are we going today?
I'd like to go to 7:30.
Okay. All right. Cool.
Okay, so that, I hope that's clear. I mean, if it's not clear, you can go over it again, but it's all based on this diagram. That diagram says everything. You see the 5 bits coming in. We're just now discussing what exactly happens. What exactly happens depending on what these 5 bits are. And okay, so more commands. Now we will go back.
I have a question actually.
Yeah.
Yeah, based on this table right here, but we see that there's like 8 or 9, what is this, 10, I think, 10 commands. But we have like 5 bits or 6 bits even, 6 bits worth of information. So that's like 64 commands. But it says complete. So is it complete or? Like,
Wait a second, I can't hear you.
Why is your cat wearing a tie, Ellie?
He's a very stylish cat.
His name's Velcro.
Thank you, Roni. Does anybody else know? Like my question?
Or why your
Are
cat's
you
wearing a tie?
asking, are there up to 64 opcode commands?
I'm saying what comes in on that command is like 6 bits. So that's 64 possible different things. But we see 10 on this sheet. But it says complete, which would generally mean that it's all of them.
I'm skeptical
Of what?
that this is complete.
Well, more interesting would be, would there be 64 options if they're assigned to opcode, in addition to the 64 options that you have if you use function bits? Total of 128.
I don't know.
Did you get your answer from one of your peers?
Is this actually complete? This is like 10 commands, but coming in on that line is 6 bits.
Let's say it's complete.
So that means we're missing another 54 commands. Like we could do 54 commands, whatever.
Right, but we don't really have much more that we need to do, and we would have to have probably more hardware. In other words, let's say we're not using. It's possible. I thought about this a lot. I never really went through and counted all the opcodes, but it's possible that we have 6 bits of opcode. It could that's a heck of a lot of commands. Could be we have much fewer. But it could be that if we would use all the permutations, we'd have to have a lot more ands over here to deal with all the different possibilities and everything we want to do and all those possibilities. So it could be that the fact that we have 6, and we could have really done it in 4, is because it actually turns out to be easier to divide it up if it's 6. To have, in other words, if we'd had 4, we might have to have more of these ands. You see what I'm saying? It could be that
okay,
we've
I guess.
wasted.
I mean, if it's 4, you could theoretically do it on 2 lines, right?
Well, we'd have smaller ands.
Yeah, but if you only have 4 options, then you could do it on 2 lines.
I'm just saying it's not necessarily so that we're using every single permutation of the opcode.
Okay.
It could be that some of them we just don't use because, you know, if we want, we don't need them, but we still needed 6 bits. Again, if we had only 5 bits, we'd be limited to 30. To 5 bits would be 32 operations, and if we want 33 operations, we already need 6 bits. So the fact that we have 6 bits doesn't necessarily mean that we have all of them in use. It could be we have only 37 operations, and we still need 6 bits.
Okay, good.
Okay, so let's say this is complete. I mean, we're never going to see anything more complete in the context of this course. So yes, this is complete. More command. Although again, we're not discussing every single command. There are commands that we don't discuss in the slides, but which you should think about how they work. Which is, for example, jump register. I think in the homework you have a discussion of that at one point, maybe in the next homework assignment. More commands. Now we will go back to the sync. In other words, you have to, the homework is a very good preparation for the exam. Put it that way. Now we will go back to the single cycle diagram and show how it works for an add command and a branch command. Fine. In other words, how the ALU is going to be controlled. Do this by setting the ALU controller outputs correctly. I wonder, why do I write like that? I should have written, we do this. I don't know what I mean. One final note, you may have been wondering, how do we send only certain bits of the instructions to various input lines? In other words, how are we saying only these bits go there? Answer, simply only wire those lines we want to those inputs. I discussed this many times before, because to me it's like, I guess it's interesting Kiddush. In other words, these lines are physically sitting there. So that's how come only those ones go there, because we only wired those ones. We could, so here's what I'm explaining here. We could use logic gates to mask out all the other fields. In other words, we could send every bit, all 32 bits to every element, every component of the computer, and then we could mask them out. Like you block them off with logic gates. If we do, that should be an on the command. If we do an and on the command with 32 bits, but the desired bits are set to 0, then we will only see the desired bits, and that would work. But this is unnecessary since we build our chip with only desired wires reaching the desired endpoints. To some of you, everything I said might be obvious. To others of you, this may be completely baffling, what I wrote here. I hope, anybody baffled? If you are baffled.
What did you mean when you said you said that where all but the desired bits are set to 0? Can you explain that a bit?
All but the desired bits are set to 0. In other words, with logic gates, we can there's a concept called a mask. We could theoretically send all 32 bits everywhere. That's all I'm just saying here. Of course, it would be more expensive to do that. It would be totally stupid, but conceptually, you could send all the command over to the ALU. And then you could just look at the bits you want by blocking off, by setting to 0, essentially, all the bits that I don't care about. And just the bits that I care about, I'll let come in. I'll use an and with a 0 on it. If I connect a line here, let me take this. Where's my annotate?
I think I know what you mean. You take all your other lines and you plug them into an AND gate with a 0 constant.
Exactly.
Okay.
Something like that. Or I could just do like, here, I do like this. This is an electrical line, and this is a 0 coming in, and I draw my AND. So now this line, whatever this data is, whether it's a 1 or a 0 on this line, whatever it is, I'm going to get a 0 over here, because that's an AND. So I can.
And you just do that with all of the ones that you don't care about.
With all the ones I don't care about, I just do that. On each one, I go to a little AND and I block them out. So I could send everything over to here, and then at the entrance, at the gateway, I could have like a doorman, you know, a chômeur. I could have a guard at the gate, and he could let in, and he would basically block off all the bits he's not interested in, and let in just the ones he wants. But that would mean sending a lot more wires everywhere, and building a lot more ANDs. So it's just. So therefore, it's better to just wire the ones I want, and then, and if I need extra ones, get them from the controller. We're trying to say, in engineering, you're always, when you connect the carburetor, and we don't have carburetors anymore, but my mechanic tells me, but when you connect, the different parts of the car together, you could always take a long route or a short route. You could always do it, there's many ways of doing it. And you always want to choose that being designing anything, that's what it means to be a designer, is to think about the most efficient way to do it. And that's all I'm saying there. I mean, that's why this course is architecture, because it's design. We're trying to think about how that's really the main thing we should be thinking about is not just how the MIPS works, but what considerations went into planning it. And therefore, really, it's a good question that I should really think about more, which is over here, are there options that are not in use, and why did they do it this way? Why did they have why exactly 6 bits for the opcode and not 5? I think 5, well, we'll see. But so I'll think about it. I'll think about it more. Where were we? So, all right, stage 1 of execution for R-type instruction. Add, so here we're going to do our add, register, register, register. And remember, it's the RD, the destination, our SRT. But of course, when we encode it, the RD hops on the other side. The first 2 stages are identical to all commands. Fetch, the command whose address is listed in the PC register, is sent from the instruction memory, I'm saying to the instruction register. I want to add that in. To the instruction register. I mean, some people don't talk about this. I don't see it in in a lot of the diagrams, but there is a register there as far as I know. To the instruction.
Is that register shown in the diagram?
That's what I'm saying. It's not really shown in the diagram.
It's just kind of implicit.
Yeah, I've seen it in other diagrams. I mean, I've never opened up.
Can you kind of show where it would be?
It would be, yes. It would be this is instruction memory. It would be between this instruction memory and, I mean, maybe you don't really need a register, actually. I have to think about it. I think maybe in the multi-cycle, it's in the register. I take it back. In the multi-cycle, there might be a register here. There may not be a need for a register. There's this instruction memory. This is access to the 4 gigabytes of memory. And he's pulling out a particular instruction and shoving it into these lines. Now I'm asking myself, well, do we need a register there to store it? Well, let's think about that. Why would we need a register there? Let's just pull it out and immediately stick the output onto these different lines. We don't need a register.
But how would you split up the lines like that if it's not on a register?
Well, this thing has 32 lines coming out of it. And if either of those 32 lines are connected to the 32 places in the register,
okay,
or those 32 lines just run directly down here, and up here. The 32 lines, we can just, weld in our connectors and just do that directly. There's no, right. Your question was exactly what was on my mind. And that's why I said, oh, there must be a register there. But now that I'm talking about it, I realize no. And when I have seen the register there, it's been always in the multi-cycle. There, we need to store it for multi-cycles. That's the whole point. Here, we're doing everything in one go. So we don't need to store it. So let me go back and remove what I just wrote.
So what
Sorry.
exactly is the instruction memory?
Let me get
It's
rid of
just
this.
a place in memory where your
Like, what is it?
instructions.
It's the RAM or
Yeah, it's in RAM. And RAM is memory, where
right, but I'm saying
Yes.
that's where your code is. The code that you wrote.
You wrote a program that has 10 million lines. You wrote a very long program. You stayed up all night. You wrote 10 million lines. In order to run those 10 million lines, you got to put them into memory. They can't be sitting in the hard drive. They got to all be in memory. That's why your computers need so much memory nowadays, because your programs are 10 million lines long. And so you need huge amounts of memory to store everything in. You can't just say, oh, I'll just take the first half of the code and I'll stick it into memory. Actually, there's something called DLL, Dynamically Linked Library. And in that scenario, which is, it's new, it's only 30 years old. In the DLL concept, you actually load, part of the program. So you actually do load half the program. But even so, you have to load a lot of stuff. But in any case, however big your program is, whether it's 1 line or 10 million lines, it must sit in the RAM memory in order to run it. In order for me to execute those lines of code, I need to fetch them, which means I need to wheel them out of the storage room and into the primary location, into the actual place in this diagram where I can use them. So one by one, each instruction memory will be, this thing looks like a little tiny box. It may be a little tiny box, but it's connected to a huge bunch of memory. That's like your memory card reader. And he knows how to read a piece of memory into these lines. Okay?
How does it actually move up and down the memory? Or you said it doesn't have to move. It's random. It can just jump.
Yeah, it just grabs it. Well, we're actually going to learn about it towards the end of the course. Essentially,
Okay.
all the bits are ultimately, if you think about it, ultimately there's a wire going from this output line, these 32 bits of output line ultimately are connected to every single group of 32 bits. In other words, every 4 bytes of memory are directly connected to this output line. So I simply have to tell back to what we talked about before about the ands and the zeros, the 0 and the 1, and doing an and, all I have to do is essentially block out everybody except for the one I want. Right?
Okay.
I'm just saying, without getting into the details, it's actually slightly different, but essentially I have a line connecting every single piece of memory to this output line. And then I just have a lot of nands, a million nands, or not nands, a million ands with zeros on them, or not with zeros, where I can control whether there's a 0 on it or a 1 on it. And I simply put a 1 on the one I'm interested in, and only he gets through.
Is that actually the implementation in the computer?
No, it's not exactly like that, but it's similar. For now, based on what you know now, that's the only way I can explain it.
Does it like work like a big multiplexer? That the code that it needs, it kind of
I don't want to
chooses?
talk. Trust me, there's a whole discussion. There's a chapter, I think chapter 10 is all about this subject. So we'll discuss it at the proper time. But the mashal that I gave is not using a multiplexer. The way I explained it is just a lot of ands. But yeah, I mean, however you want to think about it, understand that it's physically connected. That I don't have to go scrolling through a tape drive. It's all connected to that line. That's what it means when you buy a SSD card. It's when you have a laptop that has memory that is SSD and it is there's no moving parts. There's no disk spinning there because it's physically wired, and that's why it's expensive. You ever wondered why a terabyte on a hard drive costs you $30 and a terabyte of SSD memory costs you $200 or more? That's why.
How is the moving part wired?
How's a disk drive work?
Not SSD. Yeah.
Well, it's a spinning disk, like a record player. It's really like a record player. And you have a needle, and I don't know if you know what a record player is. You know what a record player is?
Yeah, I do. We have one in the museum next to it. No kidding.
It has a movie. It's actually it's a record player, but the record is got multiple records and multiple heads. And you've got, like, imagine a stack of 100 records with 100, heads going in between each one. So I can move all the heads at once and read every single disk at that certain location. And then I can move the needle around. So it's like a record that spins with a needle that is movable. I can move it, and then I can read different sections. That's how it works.
So why is the SSD more expensive?
Because that's cheap. I only have to have wires connected to each of those heads. And then depending on where it is, it reads different things. In the SSD, I have to have wires connected everywhere. Everybody is connected to the same output. I got to build a data path. I got to build a data highway from every single byte to this little output over here. I got to build a lot of highways. You understand? It's more wires.
So.
It's more wires. That's all you can. That's the simplest way to explain it. Just more wires. If I had a direct highway from my house to everywhere I want to go, that would cost a lot of money.
How come it's so much smaller?
Because to move physical things, you require, engines and motors. Here, nothing has to move, and the wires are, billionths of a millimeter, thick. That's why we talk about nanotechnology. The thinner we can get those wires, the more information we can get. You guys need to, if you're really interested in this, study electronics. But this is the physics of electronics. This is physics of electronics. Anyway, I'm a programmer. I'm actually not an engineer. I just have a lot of respect for engineering. Okay. The command, my real field is Unix. So this is not actually my trained field, but it's my favorite thing at the moment. It's my favorite topic. Anyway, the command whose address is listed in the PC, so we said, is sent from the instruction, the command is sent from the instruction memory to where? To the lines, to this picture, to that diagram. The opcode bits, and then what happens with it? The opcode bits, which is the MSB, the most significant bits, are passed to the control unit directly, which we saw in the diagram, which produces control signals with appropriate values listed in the table. Since this command has no jump, the control line branch will be 0. It's not a branch command, so the branch line will be 0, resulting in PCSRC being 0. So let's see that. The branch line here will be 0. And see? What is this? PC source. Sorry, I misread that. The PC source would be 0. Where do we see PC source? We didn't discuss PC source. This mux the branch here, the branch will be 0, right? So that branch comes into this gate, this AND, which means that we're going to get a 0 coming out for sure, which is going to be this line is the PC source. He's going to decide whether the PC is coming in straight. See, here's the PC plus 4. He's gonna come in over here, and if this is 0, then I'm gonna choose 0 over here, and I'm gonna send out the PC straight without it being the result of the 16 bits sign extended. So this is the PC source. It's this line here is the PC source.
And what is a PC source?
This
Sorry.
line.
No, but what what is it?
This line is called the PC source, and it decides whether the new PC that I'm going to go to on this command, the following command, is going to be the computation of the PC plus 4, or is going to be the computation of the jump of the branch, which I took over here. I did 16 bits, I signed extended it, and I put it up here, I shifted it left, and I added it to the PC, and I got some other number. I did the PC
Let's
plus.
tell the next line. Okay.
You understand? The next line is either going to be the normal PC plus 4, which is coming through on this here. Let me get my drawer. The PC came over here. This is the PC. Well, I can't. It's hard to draw P. P. C. And then this is PC4 plus 4. He's coming all the way here. And he's also going here. And he's coming there. And that, if PC source, this is PC source, this line. If PC source is 0, then I will take the regular PC plus 4 and make it go out here. And this line will come out here and into this mutex. And this jump will then decide, the jump source will decide whether to let it continue on. Well, this is going to have to be 0 also, so that this will be able to continue and go all the way, hopping along here, and become our new PC.
Can you clarify something?
In order for that to happen, there needs to be a 0 on this line. And a 0 on this line. And this we're going to call the jump. This line, we're just going to give it a name. We're going to call it the jump source. You know, is if jump source is 0, that means we're not jumping. If branch source, if this one is 0, then it means that we're taking the 0 at that point, which means we're also not branching. So if it's not, if you think about it, it makes a lot of sense. You can almost read it. If it's not a jump and not a branch, then it's a regular PC plus ARBA, and it goes plus 4, and it goes to here. So that's what, yeah? That's what I meant when I wrote way down here. Here, let me get rid of these things. So the PC source, wait, okay. Oh, how did I go? That's interesting. So what did I say? Oh, I want this mouse. So the opcode bits are passed to the control unit. Maybe they can play in the hall. Here, I'm gonna go a different room. So the opcode bits are passed to the control unit, which produces control signals with appropriate values. Since this command has no jump, the control line branch equals 0, resulting in the PC source line also being 0. And that makes that the MUX, the multiplexer, will select PC4 so that the PC will indicate the next instruction to be performed and not be a jump and not be a branch. In jumps and branches, the PC will be altered again in a later stage. Note, in the fetch step, the PC value will always advance to PC plus 4. Is that clear?
Yeah. Or for me, it is at least. I don't know for other people. Something that I'm just wondering about, maybe it's obvious, but what's the difference between jump and branch? I guess in my mind, they're still pretty similar.
Well, conceptually,
Branch is conditional, no?
What?
Isn't branch
conditional?
like, yeah, it's conditional.
Yeah,
It's like an if. Jump is jump no matter what.
Yes, that's true. Jump is unconditional. It's an unconditional jump, and branch is a conditional jump. That's the programmer's perspective.
Jump can go much farther, right? Jump can go like
yes, jump can go much farther, but it also has its limits.
30 bits or something.
No, it can go, well, no, it can't go anywhere. It can only go 28 bits.
28 bits is pretty good. Branch
can copy the last 4.
Something like 16 or something.
Branch can go 18 bits.
18.
but branch is more flexible. Branch can go, it can always go forward and backwards from wherever I'm standing. That it can always go forward and backwards wherever I am. It can go forward or backward 18 bits of movement.
Because it doesn't copy the first 4 most
because it doesn't
significant
copy
bits.
the first 4 of the PC. Whereas the jump, as we saw in the homework, can sometimes, even though it can jump further, it's limited by whatever the PC is, and it sometimes will reach a border. It has a hard edge. Whereas
so you're able to remind me just
wait, I didn't. Can you explain that again?
Sorry.
Well, in the homework we did a branch, and also in my slides I did an example where we do a branch to an impossible location, because since the branch, we do a jump to an impossible location, because the jump always has to jump within 28 bits of the PC, which means whatever the most significant 4 bits of the PC are, is going to limit how far we can move. So if we're just at the edge, if the PC is 0, 0, 0, 0, 4 zeros is 0, F, 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 whatever, all Fs, and then a 0 at the front in hex. So I'm going to have to grab that 0, and if I want to go 1 step forward, I can't, because 1 step forward means to location, 1 instead of 0, 1, and then 0, 0, 0, 0, 0, 0, 4, let's say, or 3. So I
And why
can't
is
go
that?
there because I'd have to change because the PC won't let me. The PC is stuck at 0.
But it's only 1 bit over, right?
Exactly. The jump has, like I said, has a hard edge. The jump, if it's at the very end of the PC's range of what the PC will let me go, then to even go 1 step forward is impossible.
What
That's
does it
I'm
mean to
explaining.
be at the? Oh,
What?
okay. Like
Because-
I think I get what you're saying. That the first 4 bits of the PC are like I guess
Are a
immutable
wall.
would be a word.
They
Like
unchangeable.
they can't change.
They're unchangeable, and
But I guess
therefore,
functionally, I don't understand why that is.
because it's hardwired like that, it's built like that. That's the way they
But
built it.
branch can.
Branch can, because branch doesn't do any append. It doesn't stick on the PC to the front of the command, to the front of the location. It adds the
branch-
PC. It does an addition,
Oh,
which means I can
but
take 0 FFFFF and add 10 to it, and I'll get 1 0 0 0 0 0 0 10. You know, or
jump
9.
will like concatenate the first 4 bits of the PC to
Exactly.
the 28 bits of the
Jump
command.
does a concatenation, and whenever you're doing concatenation, you're stuck with whatever you're concatenating. But when you're doing an addition, well, I don't care if it's 0. Now it's going to be 1. Because
So just to clarify that, just to clarify that, so the difference, so that at that point, the difference between a jump and a branch is that a branch will say how much more forward to go, and a jump will say which actual location in the PC it should go to.
Yeah, you could say it like that. Yeah. Yes.
And then practically, when writing code, is that a distinction that we should keep in mind?
Wait.
Or
Well,
the computer
the
handles it for us?
the simulator will help you, and practically you're starting at zero essentially. You're not going to worry about it. You're not going to get that far. You're not going to write anything that's that big, but theoretically you should worry about it. But I want to correct something that Yitzhak said. In the end, they're both absolute jumps. In other words, after I do all the computations and I calculate it and I have the number, it's an absolute, I'm jumping to that number. But anyway, but you're right. I mean, you're also right. Let me go on. R-type stage 2 decode. This was an R-type, right? So we haven't done stage 2 yet. So register RS and RT are read by the RF into read data 1 and read data 2 respectively. Well, that we knew. That's nothing new to us. We go over here and that comes out here and here, boom, into there, and the data that's read goes into the ALU. That one and that one. Are read by the RF into the read data 1 and read data 2 respectively. RS is passed directly to the ALU and the processor performs a sign extension on the offset field. So RS, do we have it? RS and RT are read by the RF and put out there. Okay, the RS is also passed directly to the ALU. I'm going to add the word also, unless and probably I'll end up removing it again, but its RS is also passed directly to the ALU. The processor performs sign extension on the offset field. All right, let's look at it again. Let's look at the picture. The RS, remember the order? It's RS, RT, RD. So RS is going to be this bits, the 25 to 21. So RS goes into here and comes out the data at that location into the ALU. The RT goes into here and the data comes out here. It goes into a multiplexer, which then will decide whether to pass it on to the ALU or to pass something else on. But where else does the I say that the RS also goes to assign to, right, let's directly to the ALU. Oh no, so it is, see, I'm gonna take it away. What I mean is the RS, the read out of the RS. It really should be, you can write that, or you could also write it like this. The read data 1. The thing that the RS produced is passed to the, let's see if that's right. I think that's right. Maybe I don't have the diagram right here also. I don't see where it's going to assign extender. What did I say there? Ah, sorry. The RS is passed directly to the ALU. Well, that's what we see. The RS is coming out. In other words, the read data 1 is going directly to the ALU. What else? Additionally, we should have that word. Additionally, the process performs a sign extension on the offset field. Over here.
How could you tell that that's the RS on the? How could you tell that's the RS on the circuit board?
Wait a second. On the offset field, here's the offset. This is the offset 0 to 15. It does this sign extension. So that's all I'm saying. This comes out. How do I? Gets sign extension. The offset here gets sign extended, and the RS goes through here and is added to the ALU. Now you're asking, how do I know that's RS? Well, because the that's the order of the RS is the leftmost register. Then comes the RT, then comes the RD. True? If you remember the true. So RS is the bits 21 to 25. Because instruction is 26 to, so that's the leftmost one, that's the RS. And if it's in read register 1, then the data it read is going to be in read data 1. Right? This is read register 1, that's the register to read, and that's the data that was read from that one. So this is the RS. In other words, I called it the RS because
so when you read data is the data that it gets from the register 1?
Exactly. It's the data it got from register 1. You could call it, that's why I say you could call it read data 1. You could call it register 1's data. But we know that register 1 is the RS, so we can also call it that. That's why this correction is actually good. RS, which is actually the read data 1, is passed directly to the ALU. And I'm going to put it here. You know what I'm going to do? I'm going to write it like this. The processor performs a sign extension on the offset field. Also, these are the things that happen in this stage. Stage 3. Let's see, wait a second. Well, I don't know if we're going to finish, but stage 3, we're not going to finish. Stage 3, the control line source ALU being set to 1, to 0, causes the C mutex to select read data 2 lines and transfer them to the ALU. So we have to go back up. And the ALU source, that was what we talked about, being set to, what did it say? The ALU source ALU or ALU source, being set to 0 causes it to select the read data to line transfer. So the ALU source is going to be set to 0, and it's going to choose the read data to continue on the way. Right? This will go out because of this. Now, why do you can say, well, how do you know the ALU source is set to 0? Well, we're talking about an R command. What was the command? It's an add. We're trying to do an add. So if we go over here and we look, no, not here. Well, ALU source set to 0 on an R format. Kind of already did this. Okay. According to the ALU control table, operation ALU is going to be 10, and the function field value is 32. Let's see the ALU control value. If it's an add, it's going to be 10. ALU or 10. ALU operation. And the control field is 32, and the function field is 32. That's it for an add. These values go to the ALU controller, and this unit outputs 0, 1, 0. That's what we see in this table, 0, 1, 0. Where are we talking about in the diagram? We're talking about here. The ALU operation is going to be 10. 10 is going to cause him to look at the instruction over here. Remember, that's what we said. If it's 1, 0, then we look at the instruction over here. And since it's 32, we're going to put out 0, 1, 0. Question? Somebody have a question? I mean, I didn't hear anything, but now is a good time to ask a question if you didn't get something. Okay. So these values go to ALU controller, the unit outputs, we said that. The code is interpreted by the ALU as an add request. Well, that's true. As a result of this code, the ALU performs RT plus RS. Well, we just, right, we got, in other words, that output line, read data 1 and read data 2 that went into the ALU are now being added together. The result is transferred to the mutex, to the multiplexer. And the multiplexer controller is set to 0, so the output is RS RT. What did I say? In other words, this output goes down here. We're ignoring this for the moment. Why? Because this line, this memory to register is going to be set as 0, and therefore this is what matters to us, and he's going to go out here and through here to right. All right, it's 7:30. I want to stop here. We'll pick up from the stage 3 next time. Anyone want to ask a question at this point?
I was working through the homework.
Yeah.
What is that? The one where it asks which of the following commands won't do anything will be an NOP.
Yeah.
And I was wondering if you could confirm my assumption that the registers that are being referred to there, encoded there, they're assigned 0 value because we're starting off at the PC.
Well, all the registers start off at 0.
Yeah, because nothing's being assigned to them. No command is assigning anything.
Well, let's look at the homework for a second. You're
First one
talking
is an
about
add command.
You're talking here. Well, they're all stored in address 00, and you can assume all the registers are 0 at the moment. And yeah, I don't know. So, what's your question? So, repeat your question.
I'm basically curious about the encoding that we're looking at, because when I looked it up, I'm confused between function and opcode.
Well, it's like this. In these 3, they start off with 6 zeros, so they're all R type. So in order to know what the command is, I got to look at the function, which is at the end over here.
Where's the MSB?
This is the MSB is most significant bit, and LSB is least significant bit. Or this is the most significant. This is 32.
That's 32.
Or 31, whatever. 31, 0. So if these are all zeros, that means the opcodes are all zeros. I mean, yeah, these 6 bits. So therefore, I look at the 6 bits at the end here, and I know that this is, 1, 2, 4, 8. That's 8. 8. I don't remember what 8 is. Maybe it's a jump register. I don't remember. These are the commands, and you got to figure out what once you know what the command is, then you know what these fields represent. Any other questions?
Wait, just to tack on.
Yeah.
When I started this, I looked up what's the opcode of 6 zeros, and I got it's a shift left logical.
No, you made a mistake. 6 zeros. 6 zeros. We have to remember the opcode field is 6 bits. In any chart that you look at, it's going to show you just the value of those 6 bits. So, for example, let's see, Mips, green card. And if I look at any R type, see R, it says 0 over here. 0, 0, 0. These are not, here's an R type, 0. Yeah, jump register. 8 is jump register, like I said. So the 0 here means 6 zeros. And the 08 means 6 bits whose value is 8. So that would be 0, right? If it's not a jump, if it's a jump command, for example, not a jump register, but a regular jump, then the opcode is 2. And so I know that it's 2, and I don't have to look at a function code. That's why there's no function code written here.
Why in lots of these, like for example, load byte unsigned? Not that I know what that is, just like in the opcode function column, there's nothing, like there's no slash. It just says 24 hex.
that isn't the opcode function. That is the opcode function is written there. It's 24. If I write 24, that means load byte unsigned. It's not an R type, and therefore I do not have anything written after the 24, which would normally be written, which would be the function.
That. So when
That
there's a
24
number,
is not the function. That 24 is the opcode. If there's just one number written there, it's the opcode. If
and
there's
what's
two
in the
numbers,
0 through 5 in that one?
what?
And what goes in the 0 through 5 in that command? Not the actual bits, like what
The
what
offset.
information is there?
The offset. It's a load byte unsigned. It's an I type. You're loading a byte. You're giving it an offset. Sign
Okay.
extended immediate. There's an immediate value there.
All right.
In other words,
Good.
in the 16 bits, you've got the rightmost 16 bits, the right half of the command is the offset. Normally, in an R type, the function would be in the right-hand side. But there's no function here. So therefore, those same bits have a different meaning. Okay? We're good? Question?
I'm wondering, was this class dependent on yesterday's class? Because I didn't feel like I didn't get 90% of it.
Yeah, it kind of is dependent on yesterday's class. Go over yesterday's class and then read it and then do this class. I mean, yeah, it's kind of dependent. I mean, I gave enough information that you could kind of follow along if you weren't in yesterday's class, but probably you wouldn't be able to. Go over yesterday's class. I put it on Moodle.
I mean, what is? Do we need to know this class? I mean, is there any homework that's doing it that uses it?
Well, you need to know everything that I'm teaching. I don't understand the question really.
Okay, like which homework uses this class?
The next homework, I think.
What do you mean homework 2?
3, number 3, which I put up, but it didn't assign. It's going to be due after Pesach.
Professor, are we able to do this in pairs? Did you say that for these homeworks, or did you mean that for the labs?
Listen, you can work in pairs, or I don't mind if you work in pairs, but but I want each person to hand in his own thing. And you can work. It's sometimes helpful to work together with other people, but ultimately you're handing in your own version of the work that you did. You're not copying from somebody, and yes, you can work in pairs, but not hand it in pairs.
Thank you.
Sure.
Like, what is the subject of today's class? Like, if I'd Google it or YouTube it or something.
The data path of the single cycle Mips architecture.
Data path, single cycle, Mips architecture.
Yes.
Okay,
But
thank you.
we went into a great amount of detail, which I doubt you'll find in much anywhere else in Google. But maybe you will.
Well,
There's an excellent 10-minute video on the multi-cycle that I know about.
Shall I say that again?
There's an excellent 10-minute video on YouTube by a guy named Mohammed, but he's an American. And I mean, his accent is American, and he explains the multi-cycle. But we're not doing. But it's very similar, but it's different. But you could watch that also. But we're doing single cycle at the moment, which means everything happens at one clock cycle. Okie dokie. All right, so I'll call it a day. Thank you guys. And how do I stop video? Okay,
Thank you, Chavez.
sure. Travis, so how do I stop the whole thing? Oh, stop share. There, and now end meeting.